Good day. You have a sheet that says chemical bonding, polarity of molecules, and I think this one's a little more useful than the previous two in that we're going to take the information from the previous two sheets and apply it when we look at some structural diagrams. So we're going to go one by one. Here's H2. There's its lovely Lewis structure. We know it's linear. So we do H, and that's a single line to another H. Well, we love it when we have two atoms and they're identical. That means there's equal sharing of the electrons. It automatically is going to be non-polar. And it reminds us that diatomic molecules for any element, such as oxygen, nitrogen, chlorine, all those, they are going to be non-polar molecules, equal sharing. On the other hand, if we have two different elements, what we have here, in this case with HCl, is Cl has a greater electronegativity. So we have a polar covalent bond. And this molecule, we only have one bond. And so in fact, we would put our HCl and we draw a line right through it. Now these lines aren't quite perfectly done. They should have a little thing here going along. But what this tells us is that the electrons are spending more time with the chlorine, and since they're pulled that way, the chlorine part's the negative part of the molecule, and the hydrogen is going to be the positive part of the molecule. Carbon dioxide's interesting. We've got its Lewis structure. You can see it didn't photocopy quite right, or it's got hole punched there. We need a little O right here and two more lone pairs on it. And what we see is we end up with a linear shape. This is going to be AX2. So oxygen's more electronegative than carbon, so this oxygen pulls electrons away from the carbon, and this oxygen pulls them, and because it's linear, it pulls them in exactly the opposite direction. And they have the same magnitude. So look, this is AX2. That's a parent shape, and this is a case where it can cancel out and it becomes a non-polar molecule, even though it has polar bonds. Here's Wawa, and there is our two hydrogens and oxygen, and we go, well, V-shaped, hate that name. Much better called bent. So they've drawn it with this bent structure, and we have a vector, the oxygen pulling towards the hydrogen there, the oxygen pulling towards, from the hydrogen, the electrons, I should say, involved in the bond. And what happens is the net effect is our overall vector for our dipole splits the middle. It goes right through the middle, and we end up with a polar molecule. So over here, this would be the positively charged part of the molecule, and this would be the negatively charged part of the molecule, but it's just a partial charge. NH3 ammonia, we know it's trigonal pyramidal. We have a whole mess of vectors. We have three vectors showing the nitrogen pulling the electrons away from each of the hydrogens. And overall, it's going to run right up through the middle. Now you might say, what if I put the hydrogens up high and the nitrogen down the bottom? Well, the dipole would go just the opposite way. So it does depend how you draw it. And on a worksheet, on a test, you're not going to put in all of these little arrows. You're just going to put the big arrow in to represent the overall dipole. CH4, now there it looks like it's square planar. That's the problem with Lewis structures. In fact, it's tetrahedral, that we get this three-dimension, we get bigger angles than 90 degrees between them. But all of these bonds are identical. So again, we have polar bonds, but a non-polar molecule. There's no net dipole. Now, let's say we had, in that case, we have all H's, so we end up with a non-polar molecule. Let's say we put chlorines, 4 chlorines around. Be the exact same thing. We'd end up with a non-polar molecule. But if we put 3 hydrogens and 1 chlorine, now our dipole would go towards the chlorine. And let's say we put 2 chlorines and 2 hydrogens. You might say, oh, they might cancel out, but they will not. The dipole would split the difference between the 2 chlorines. This one's an interesting one because we have 2 central atoms. And we can see we have a carbon that's bonded to 3 things, no lone pairs, AX3, so it's trigonal planar. So we have trigonal planar here, trigonal planar here. So the net effect is we'd have a dipole from the left side of the molecule, one head to the right, from the right side of the molecule, one head to the left. And those dipoles cancel out. They're equal and opposite. So this is a non-polar molecule. And a lot of organic beasties are non-polar. Here we have, again, 2 central atoms. This time it's AX2. 2 things bond to carbon. No lone pair left over. Same for this one. So we have a dipole, dipole. Overall, the dipoles cancel out, and therefore it is a nonpolar molecule. So hopefully that helps a little bit in terms of going from these shapes on paper, but again, it will get easier if we actually look at models and then start looking at figuring out the dipoles from there.